For today's class, if you remember what we covered in the last class, it was something around a little bit of the linear algebra, which we covered, linear algebra part, okay, where the Dirac notation and the corresponding inner vectors inner product, then the like Hilbert space, then a little bit of the those things like that orthogonal and orthonormal orthonormal we covered, and also the orthonormal basis and why it is like very important for quantum mechanics. We covered all these things, and except that we also covered a little bit of the classical physics pitfalls. We covered on that part, and the motivation and why we have transition towards a quantum physics or mechanics. Okay, and what were the like primary observations where we have seen like Compton scattering effect, then we have seen the de Broglie case. Okay, and we also have seen the wave particle duality, that thing which was of de Broglie, sorry, wave particle duality. So this is under this, and then we have seen the double slit experiments and all. So there are and a few more, quantum tunneling and all. So all these things we have seen, and then we have seen the parts of the linear algebra, and also we covered a little bit of the qubits and the quantum versus quantum state, that kind of thing we discussed about it, and a little bit of like what is the relationship between them and what is a pure state and superposed state. All these things we covered, and of course for a 1 qubit and 2 qubit we covered the bracket notation and all, the matrix form and all, everything. So with that note, there are a little things that is left on the linear algebra as well as the quantum mechanics, that intersection part, which is based on the observables and a few operators. So, and that will lead to Hermitian operator, which is very important for us to understand. So today we will be starting with that thing. So today's agenda, you can say, what we are going to cover is primarily we will be covering the observables and operators, where primarily we will be covering the Hermitian operator, because all quantum operators are of this type, or say quantum gates are of this type. Then we will be covering a little bit of this thing. So we will be repeating this thing, like we will understand again in a more detailed way, considering that we today have a good understanding of the Dirac notation and all. So qubit and superposition and their representation. Okay, so we will be talking about this once we cover the Hermitian. Right, then this is one, this is two. Third part is we will be covering quantum teleportation, which is another part, and super dense coding. I'm not really very sure. I think in Q3 00 and 01 also we covered a little bit of that, but this will be a repetition for quantum technologies as well as per your syllabus. So we will be covering this part, and post that, if time permits, then we will enter into the Schrodinger's equation. Okay, we will be starting with the time dependent and time independent Schrödinger equation, and we will see the potential energy and all those like relationship we will try to see. So this is kind of what our objective is for today's class. Let us see that how far we can cover, because this part is going to take some time, along with the QT, like teleportation and super dense coding. And tomorrow we will be covering with a little bit of, let me also write it so that you have a like good understanding. So for day 4 we are targeting to complete the Schrödinger equation. So I guess like 4 will again be continued. So Schrödinger's we will be continuing. Okay. Schrödinger and the unitary transformation. That part we will be continuing. And also with that, we will be talking about the measurement postulates in a detailed way, and the concept of interference mathematically. That will be covered as well in tomorrow's class. We'll look into that. And we will be covering our next agenda is for day 4. Like day 4, topic number 6 is we will be covering a little of that thing, the density matrix, the density matrices. That part we will be covering, and how the measurement varies, like its relationship with respect to the measurement theory. So we will be covering this thing, and we will target to cover a little of the Bloch sphere and qubit representation, or say quantum state representation in Bloch sphere. I guess this is what we can target of covering. And in the last day, that is day 5, we will primarily look into, that is the topic number 8 is, we primarily will look into the quantum. Once we have the detailed understanding of all these things, we will be little talking about the quantum PMD, or physical machine description, but a little bit of the architectural parts we will be talking about. Okay, where there are like trapped ion, what are the like qubit architectures we have, trapped ions, photonics, and followed by the superconducting qubits, neutral atom, okay, and so on, whatever are there. A little bit of discussion we will be having on this, maybe for 20-30 minutes post, and followed by that we will be only talking about the quantum gates and quantum circuits in a detailed way. And we will look into arbitrary quantum circuit synthesis. Quantum circuit synthesis. So this is what, in a broader sense, there might be a little alteration as per the requirements, but this, in a broader sense, is what we are going to cover in all these 3 days. And also one more thing I just missed here, that is for today. Before the teleportation and superdense coding, we also are going to be talking about the no cloning theorem. So all these things together will give us a good essence of the quantum technologies as well as computing. So that in your QT03, you can exactly continue from this and you can enter into the quantum algorithm part in a detailed way. Okay. So this is what is the like to-dos for us for the 3 days. This is in day 3. And this is what we covered in day 2. And day 1 was introduction primarily. Okay. So on that note, let us start for day 3 as per our objective. So today first we will be talking about just a quick recap. I hope you right now know that what is that orthogonal matrix, and how it is like if two vectors, when we can call it orthogonal, right? If their inner product is 0. And then the orthonormality, where orthogonal property has to be there as well as it has to be normalized, right? And ket notation is basically the column vector representation, bra notation is basically the row vector representation. And psi, that generally these are the like Greek mathematical symbols with which we use in ket form, like ket psi, ket phi, just to represent a quantum state. So on that note, let me start. So observables and operators. Okay. Now, what is observable? Observables can be either the position or the momentum or the energy, etc. And these are represented, that is, observables are represented by some linear, okay, and self-adjoint operators. Self-adjoint operators in that infinite dimensional vector space, which is also complete, known as Hilbert space. And this is often written by this symbol. And an operator acts on a kate, okay, the kate, this thing, and produces another vector in Hilbert space. Okay, that means an operator is something that, say, it operates on quantum state which are represented with the kate, say quantum state 1, and produces another quantum state, say 2. And quantum computing is nothing but the quantum state transformation from the initial state to the final state through several intermediate states. Okay, so it's like, say, quantum state 1, then quantum state 2, on, of course, on some operator, then quantum state 3, followed by some quantum state I, followed by again till the quantum state final. And this entire thing is basically what we refer as a quantum computing state transformation. So unlike classical, where we primarily deal with some variables, some function calls, and all these things, here, whatever operation that we do through some operator, which operates on the kate form of a quantum state, basically does what? Does the transformation of one state into another. And through several sequence of transformations, we got the desired quantum state. Now, once we get the desired quantum state, we measure it in order to get the desired outcome. This is something that we follow. So this is known as the quantum computing state transformation. Okay. So it looks like this. Say A is an operator that acts on the quantum state psi to produce a quantum state, say phi. Quantum state 1 and 2, psi and phi. Similarly, if it operates, say, on the particular B is the operator, and it operates on likewise on the bra notation. So it will produce something like, say, this lambda. But definitely this particular format is very dominant. And this is what we always refer. Okay. Now, operators have some property like they are linear. Like quantum operators are linear. What do we mean by that? That means if A is an operator and if a state, a superposed state is in this form, alpha ket psi plus beta ket phi, say, then it similar to alpha, which is the expansion coefficient, and operator times psi plus beta operator times phi. This is the linearity. There is another operator known as identity operator. which means that I on psi will produce the same state psi. When it is required, when we need to do no operation. But maybe using this, we can get rid of the problems associated with decoherence. Okay, just like we do, like we install cycles in pipeline in computer architecture. Similarly, something like that we can use here as well, so that it works as a like signal restoration purpose. It can be used. Okay, or say quantumness restoration purpose. It can be used. And second one is two operators are non-commutative. And you also know that matrix multiplication is also not commutative in nature. So two operator, this is equals to AB minus BA. If you do that, then that is not equals to 0, which means A and B are not commutative operator. Which in an easy word, say, right now you do not know, but say for example, if I just ask you, first you apply a not, then you apply a Hadamard. What are they as of now? You don't have to know, just know that they are two quantum gates, say two operators. So first applying not, then applying Hadamard is not equivalent to first applying Hadamard, then applying a not. This is the meaning. Okay. And if AB is equals to BA is equals to I, identity, then B is A inverse. Now this is all that we know from the normal principle of like matrix and linear algebra. We know this thing. Okay. Now is the adjoint of an operator. And its representation, of course, in quantum notation. Suppose I take a inner product, say I take an inner product. Inner product is also known as scalar product. Why we know? Either it can be 0 or 1, that is, this is this thing, something like that. Okay. So suppose I take an inner product or scalar product of phi with a vector psi. That means it is like this, phi, an operator, and the vector. Then this is equals to A dagger, this is the symbol, psi and phi. And this is known as dagger or dagger of A, say. And A dagger, whole dagger, just like A inverse, whole inverse, is equals to A. So this can be interpreted as in this way, say the dual of ket A psi is basically what? Psi A dagger. Okay. This is the dual of A ket psi. That is psi A dagger. And then this phi A psi, which was A dagger, phi psi, this thing. That means this can be written as, now from this we can write it down, that psi A dagger phi is equals to A dagger. I'm just replacing it, nothing else. A dagger whole dagger psi phi. Now A dagger whole dagger is A, which is A psi Fine. Okay. Now, when something like this happens, we call it a self-adjoint operator. So, self-adjoint operator is one class of operators in, say, quantum mechanics, which is or which represents any physical observables, meaning the position, momentum, or energy. And these self-adjoint operators are also known as, alternatively called as, Hermitian operators. Hermitian operators. Now, if you know that the like the in the real space or the real number space, whatever is we call as a symmetric matrix or symmetric operator, in the complex vector space we call it as a Hermitian one. So there is a relationship between this. So the symmetric is Hermitian, the skew symmetric is skew Hermitian, right? So there is a relationship between them. So Hermitian operators, these Hermitian operators have the property that A dagger is equals to A. That is, they are self-adjoint. Now, by saying that an operator acting on a vector gives another operator in the same space, what I'm trying to say is, say by saying an operator acting on a vector gives another operator in the same space, that is the same vector space. If this is true, then a general representation of an operator is like this. This is the representation of an operator. This is, say, A cap is equals to alpha then beta. Now you remember or see, this is the Ket bra notation. Let me take a small example and understand that how this operator actually looks like. Okay, say I'm taking Ket 0. So this is your 1 0, and I'm taking then, say, bra 1, which is, say, 0 and 1 in this form. Sorry, not like this, or this is basically row vector form. So that means Ket 0 bra 1 is basically 1 0 followed by 0 1. So this is a 2 cross 1 matrix. This is a 1 cross 2 matrix. So the result will be definitely a 2 cross 2 matrix. So this is 1 into 0 1, 1 into 1 1. Sorry, 1 into 0 0, 1 into 1 1, 0 into 0 0, 0 into 1 0. So 0 1 0 0 is a matrix. But what is more important here to understand is, where we have done the bracket notation, it was the inner product where we used to get a scalar outcome, only a single value, because it was 1 cross 2 or 1 cross n followed by an n cross 1 matrix multiplication. So the result was a 1 cross 1 matrix, which is a single value. On the contrary, whenever we are trying to look into some quantum operator, the definition is we should be doing a Ket notation followed by a bra notation. And you can see it will be a square matrix. So it is a like Kate is basically an n cross 1, and Brown notation is basically a 1 cross n. And if you multiply them, you will be going to get n cross n matrix. So this operator is known as the outer product form instead of the inner product. So by now you know at least one thing, that is in quantum or any quantum operator is nothing but a n cross n, that can be anything, matrix. This is the definition of a quantum operator. So whatever and what is quantum operator, whenever we are looking into the quantum gates, we will understand it in a even detailed way. Quantum gates are nothing but the quantum operator. So any quantum gate here is basically a matrix because of the outer product form. Okay. And this is the outer product form. So it all looks like this. Say 1, A2, and likewise. Sorry, it's 2, 1. Say it's 1, 2, 1, N, A2, 2, 2, N. And likewise it is ANN. Something like that. This is the generic representation of a quantum operator. So that means if alpha followed by this beta, which was operator, and then we apply a scalar, so this was the operator, then this is another one, we will be getting another vector in the, we will be getting another vector in the, with certain say amplitude, in the same Hilbert space. These are the generic representation. Okay, so it looks something like that. So now an n dimension, sorry, yes. So now say an n dimensional complex vector space is something like this. We represent it using this, or alternate representation is this thing, any form. So in research paper, you can see actually any form. So in now, say the n-dimensional complex vector space Cn is a generic one. So let me take C2 or C square. It they are 1, 0 and 0, 1. Remember the orthonormal basis and all those things. Now, this is not very, this is not unique representation, of course. They are not unique. Why? Say I'm taking, say 1, 1 is also something that I'm considering, or say 1 minus 1. What is the problem with these things? They are not normalized. And so that means we have to normalize it. And how we can do that? Using some normalization metrics. So this is basically 1 by root over of 1 square plus 1 square. That is 1 by root over of 1 plus 1. That is 1 by root 2. So once you write 1 by root 2 and 1 by root 2, they become normalized. Or similarly, 1 by root over of 2 and minus 1 by root over of 2, they are also normalized. But on the 1, 1 and 1 minus 1, they are not normalized. So if we have to take the normalized version in C3, then it will be 1 0 0 0 1 0 and 0 0. Okay. And so the general representation of this thing, that is a ket followed by bra notation. This is known as outer product form, as we have seen, and also it is called the matrix. So this is this, or the matrix direct form. These are the two names that we use for the operator. And also this is discovered by Kronecker. So it's known as Kronecker product, also known as direct matrix product. So all these are names of this thing. Okay. Now say I have a matrix A, which is like 1 plus 2i, then minus 5i, then 3i, then 4. So it's a 2 cross 2 matrix. Then what we have to do? First we have to take the transpose of A. Transpose means rows and columns. Okay, that will be interchanged. So let me do that. So that means it will be just the row will be now the column. The column will be the row. Right? Then we have to, the second is we have to take the complex conjugate. That means from this to this, then it will be 1 minus 2i, then minus 3i, then this is 5i, and the complex conjugate of 4 is only 4. Okay? Because 4 can be represented as 4 plus I into 0, and its complex conjugate will be 4 minus I into 0. Anyway, this is also 4, this is also 4. So that is why in real numbers, complex conjugate is the number itself. And this is something which is the A dagger. Now the question is this matrix Hermitian? A matrix? The answer is no. Therefore, A is not a Hermitian matrix, as A dagger is not equals to A. So this is not a self-adjoint matrix or a Hermitian matrix. But any quantum operator, if that is represented in the matrix direct form, which is a matrix, then that is definitely a Hermitian matrix. Now let me take one more example where it is a Hermitian matrix. Say I have taken B, which is say 3, 2 minus I, minus 3 I say, then it's 2 plus I, 0, 1 minus I, then it's 3I, 1 plus I, and 0. Now let me follow those two things. First is the B transpose, which will be 3, 2 plus I, 3I, 2 minus I, 0, then 1 plus I, then minus 3I, 1 minus I, and 0. Now let me take the complex conjugate of this thing. Okay, then it will be like 3 is 3 itself, 2 plus I is 2 minus I, 3I is minus 3I, then this is 2 plus I, 0 is 0, this is 1 minus I, this is only 3I, this is 1 plus I, and this is 0. Now what is B transpose complex conjugate? This is nothing but B dagger. Same thing. B dagger is nothing but B transpose its complex conjugate. And if you see, this exactly is equals to B. Therefore, B is a Hermitian matrix. Why we are learning this Hermitian thing and all? Because the self-adjoint, because any quantum operator is Hermitian. Okay. So this completes the basic mathematical postulates of quantum mechanics, which are associated with the linear algebra things. What we need to know: the Dirac notation, the bracket form, then followed by the inner product and the outer product form, then the orthogonal, orthonormal basis, followed by that like properties of orthonormal basis, where we have seen the expansion coefficients or the projection operator, followed by the Hermitian or the self-adjoint matrix. Now, so in a very nutshell, what are the postulates that we covered is quantum mechanics. Say, postulate number one. Postulate number one is every physical system every physical system is represented by a ray, okay, in an abstract inner product space. We know now what it is called, like Hilbert space. And postulate number two is that this is very important, there is no difference between h psi and some scalar multiple of h psi, where this is a scalar multiple or say a complex number. So there is fundamentally in realization level no difference between psi and c followed by psi. And because of that, quantum states are actually represented by a ray in H, not a vector in H. Okay, so this is what the first part that we committed, that this is the observables and operator part. So now we covered this part. So next is we will enter into qubit superposition and representation. So we covered a little of these things, but we will be again looking into it in a deeper way. So now it's the part 2 that we will be starting. That is the qubits, quantum states, and their representation basically. So qubits versus quantum states. Okay. So if you remember what was the relation, if we have n qubit system, n qubit quantum mechanical system, then maximum number of superposed states. Okay, or rather you can say it number of states in superposition. This is even better. Superposition is basically 2 to the power n, and we represent it with the capital N symbol. This is the general notation for quantum states. So capital N is the number of quantum states, and 2 to the power n is also the number of quantum states, and small n is the number of qubits. Okay, so that means if I have n equals to 1 qubit, then your n can be 0, ket 0 and ket 1. If you have n equals to 2 qubit, then number of states or max, n max, that is 0 0, 0 1, 1 0 and 1 1. For n equal to 3 qubits, the maximum number of states possible are 0 0 0, 0 0 1, 0 1 0, 1 1, 1 0 0, 1 0 1, 1 1 0 and 1 1 1, and so on. This continues, right? So now the representation, ket 0 was 1 0, ket 1 was 0. Done. Ket 0 0 was 1 0 0 0, ket 0 1 was 0 1 0 0, ket 1 0 was 0 0 1 0, and ket 1 1 was 0 0 0. There should not be any difficulty in understanding this. We covered it. This is the 3th position, and this is the 0th position. Same logic, right? And also, ket 0 0 can be written as this. They are same thing. Why? Because this generally represents a duality. Okay. So similarly, if I have to write this one, ket 0 0 0, then that will be 1 followed by all the 7 zeros. 1 0 0 0 0 0 0 0, right? So that means 0 0 1 can be written as, now let me write in this way, this, or you can write it as transpose, no issue, anything, any one of the like notation you can follow. Then 0 1 0 will be 0 0 1 0, then all these things. Okay, 0 1 1 will be 0 0 0 1 0 0 0 0. Let me write all of them. So this is the 3rd position, so here it is 1. For this one, it will be the 4th position, where you can find a 1. For 1 0 1, it is the 5th position, so 0 1 2 3 4 5 6 7. Okay, and 1 1 0 will be 0 0 0 0 0 0 1 0, and 1 1 1 will be 0 0 0 0 0 0 0 1. Okay, so this is the mapping that we have. Now let us understand a little of the in the like superposed form as well, because all these things are pure states. Let me have this. Ket psi is alpha ket 0 plus beta ket 1. So psi is the 1 qubit superposed quantum state comprising of 2 basis states, 0 and 1. Okay, now if this is the one, then this is basically, if you check it, it will be in uniform superposition, again, let me write it, meaning both 0 and 1 are equiprobable. I'm little fast here because we already covered a part of it yesterday. So I hope you can cope up with the speed and as well as you can match with what is going on and all. Okay, if you have done some little like study of the last class. So in uniform superposition where both are equiprobable, it is nothing but 1 over root 2 get 0 plus 1 over root over of 2 get 1. So that means alpha is equals to beta is equals to 1 by root. What are alpha beta? They are the probabilistic amplitudes. Right? So we, instead of the projection operator and all, or the expansion coefficient, will be now onwards using the term probabilistic amplitudes. Okay. Then the probability of occurrence of 0 is 1 by root 2 whole square, which is half, which is equals to 50%. And probability of state 1 will be 1 by root 2 whole square equals to half equals to 50%. So both are equiprobable. Now, if I say you, so this is the uniform superposition. Does it always mean that they have to be only 1 by root 2, 1 by root 2? Not at all. Say, for example, let me give you a numerical example. Say, kid, say, I'm asking a question that there exists a 1 qubit, this is a there exists symbol, quantum system, where the probability of occurrence of state 0 is 3 times the probability of occurrence of state 1. And if, say, the state in superposition looks like psi is equals to alpha 0 plus beta 1, calculate the values of alpha and beta. So if this is a question to you, then what will be the solution? See, what is given to you? That the probability of occurrence of 0 is 3 times that of the occurrence of 1. What is the probability of occurrence? So if psi is alpha 0 plus beta 1, then probability of occurrence of 0 is basically alpha square, and probability of occurrence of 1 is basically beta square. Remember, always this is not the alpha beta, probability of alpha square and beta square. And of course we know that alpha square plus beta square has to be equals to 1. This is the normalization constraint. Simple, by the rule of probability, this has to be true. Now probability itself is, for the 0 is 3 times that of the like 1. That means beta square is equals to p. If that is the thing, then alpha square is equals to 3p. So let me write it. 3p plus p is equals to 1. So 4p is equals to 1. P is equals to 1 by 4. And that means beta square is equals to 1 by 4. Then beta is equals to half. And alpha square is equals to 3 by 4. Then alpha is equals to root 3 by 2. Therefore, the values of alpha and beta are root 3 by 2 and 1 by 2. Why we are ignoring the minus? Because it cannot be negative. Okay. Are you clear with this part? I will be just covering a little on the 2 qubit as well and the 3 qubit. Then I will be asking you the take your queries if you have any. So this was the case. I hope now you understand. So what you have understood from this is an example of a non-uniform superposition. And this can definitely happen. Okay. This can happen. Now say your psi is alpha 00 plus beta 01 plus gamma 10 plus say delta 11. Then what are the implications? What is your understanding? Let me write the understandings or the interpretations that you can have. So understanding number one is psi is a 2-qubit quantum state in superposition with the pure states 0, 1, 2, and 3. So 1, 2, and 3 means 0, 1, 1, 0, and 1, 1 with probabilistic amplitudes alpha, beta, gamma, delta, respectively. This is observation number one. Second is probability of 0, probability of 1, probability of 2, probability of 3. That is always equals to, or they will be alpha square, beta square, gamma square, and delta square, respectively. The third is by simple rule of probability. Your alpha square plus beta square plus gamma square plus delta square has to be always equals to 1, right? What is the fourth rule? If psi is in uniform superposition, that means alpha is equals to beta is equals to gamma equals to delta, which also implies that alpha square plus beta square plus gamma square plus delta square is equals to 1. So this can be written as 4 alpha square is equals to 1, implying alpha square equal to 1 by 4 and alpha is equals to 1 by 2. So that means get psi, then it can be alternatively written as half you can take as common. Then 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. And their probability is 1 by 4. That means the probability of 0 is equals to probability of 1 is equals to probability of 2 is equals to probability of 3, and that is equals to 1 by 4, that is 25%. So I am uniformly probable to either receive get 0, 0 or 0, 1 or 1, 0 or 1, 1. So all these four are the observations. And fifth is if psi is basically say A1 0 plus A2 1, A3 2, likewise say A8 okay, I have to write with this thing, okay, then 7, which is say A1 0 0 0 plus A2 0 0 1, likewise it is still A8 1 1 1. If that is the case, then in uniform superposition, it will be 8a square, or say a1 square is equal to 1. So a1 square will be 1 by 8. So this is the probability. I guess this is 12.5%. That is half of 25%. So each of these states 0 to 7 are 12.5% probable to occur. And A1 is equals to A2 is equals to till A7 will be, or A8 will be, is A8. That will be your exactly 1 by, this is the probability, right? So it will be 1 by root over of 8. Whatever be the value, that will be the value. Just you take the square root of 8, then 1 by that, whatever value we'll be getting. So this is the relation between the superposed state, uniform, non-uniform superposition, probabilistic amplitudes, and the probability of occurrence of each of these states upon measurement. Right? And this actually, I think, is a good enough for us, at least in our third class, to cover the first understanding or the commitment that we had, that is the qubit, superposition, and the representation. Okay, now I want to take a little pause here. I want to understand. If you have any doubt, we can discuss. Otherwise, we can continue. Okay. Repeat P2. Madam, can you please just explain that what your question? Repeat P2. What do you mean by that? What exactly your question is? Okay, and others as well. Okay, postulate 2. I got that. I got that. Okay, of the quantum mechanics, I guess. Yes. No, it basically says like the scalar multiple on any quantum state that actually does not create any visible difference. That does not create any visible difference in the Hilbert space to occur. So that is why we do not represent it in form of a vector. Okay, everything we here represent in terms of the rays possible or the Kate notation only that we use. Please explain the mixed state and the pure state in quantum computing. Yes, so this is exactly what we are doing. Like says for a one qubit, 0 and 1, they are pure states. But whenever you are actually using them in superposition, which is Kate 0 plus Kate 1, that will be a mixed state. Okay. Similarly, for 2 qubits, it is like all the 4 states together. That will be a mixed state. Yes, 00011011, they are pure states. But whenever you are taking all of them together, like 00 plus 01 plus 10 plus 11, then that resultant state will be the mixed state. So mixed state is after you have done your cooking. Yes, Hilbert space is a particular type of vector space, nothing else, where we just believe that any arbitrary quantum state that can be represented. That is, we do not have any hindrance in the dimensionality that we can get in of the vector space. But this is an ideological definition of the Hilbert space, just for us to understand that we can actually use any number of qubits to represent the quantum states. I will try to explain it again with the diagram. Yes. So statistical mixture, I'm not getting what exactly you mean by statistical mixture. Basically, this is the thing. Let me just, uh, okay, give me a time. Give me some time. So the case is, say you have a red ball and say the ball is like this. And you have a blue ball, which just said this. So this is your ket 0 and this is your ket 1. But say you are something like this. Say like the ball is spinning. So one position can be there where you can actually see this kind of an observation where one part is red, another part is blue. So this is the superposed state. So we were talking about 0 and say 1. They are pure states. They're quantum states but pure states. But whenever we are talking about 0 plus 1, then that is a superposed state. It's very simple. See, there is one superposed state which has two pure states in it for a single qubit operation. So superposed state is a mixed state where you possess the like possibilities of 0 and 1, all of them, both of them. That is the mixed state or superposed. Just like the finger up and down thing. Like you can have any of these combinations. So the resultant state will be a superposed. Only the possibilities. Say for example, likewise, like this, you have several balls. So say balls are like this. So this itself is in superposition. So this is 0, 1. And this is qubit number 1, say. Qubit 1, qubit 2, qubit 3, and qubit 4. So this is 0, 1. So whenever you have two qubit, let me take only 2. Now if you take a tensor product, you will be getting 0, 0. Then we'll be getting 0 and 1. Then this is 1 and 0. And then this one is 1 and 1. So that is why we say whenever there are a two qubit system together, say two photons together, then that will result into 4 states. Okay. So 0 plus 1 will look something like this, 1, 1. There will be certain amplitude. I'm not considering that. Just understand so far that this is also normalized. Because it has a property of 1, 0, which was ket 0, plus 0, 1, which was ket 1 together. So if this is psi, this is 0 plus 1 together. So this is pure state, this is pure state, but this is one superposed state. Okay. I think Satish. Uh, is it clear now? Yes. Yes, alpha, beta, they can be real, they can be complex. And the square of alpha and beta, that is the probability of finding that particle. Exactly true. Exactly that is the case. And where alpha and beta, all these things are coming, you can find it in yesterday's lecture where we actually derived that orthonormal basis and all, and then how it comes. We have just done that after the inner product thing. Okay. So anyone, if you have any doubt on understanding the pure state and the superposed one, you can ask right now. Yes. Yes. And anyway, complex is a superset of the real numbers, right? So generally it can be the complex number. So what is qubits? Then how that qubits can be used to create the quantum states. And then quantum operator is nothing but like quantum state to quantum state transformation. And all these things are physically realizable. And also like whenever we measure it, if there is a scalar multiple or say a complex number multiplication of something with respect to a quantum state, then On measurement, it does not create any visible difference. So that is another very important postulate, or postulate number 2, that we discussed. Again, on measurement, let me tell you, not numerically, but during measurement of that particular quantum state, that will not create any visible difference. That is what I'm trying to say. Superposed states are not necessarily mixed state. There can be superposed state for which trace of rho square is equals to 1. Can you refer like what rho, what you are referring as rho? I'm getting your point. Maybe you are asking something of the density matrices and those mixed states. But clearly, as of now, superposed means something like that is not pure. So I'm referring them as a mixed state. I hope you're like not getting into that technicality of the density matrices and that measurement and the mixed state operator and all those things.
Afternoon, Nivedita ma'am. Dr. Majumdar here.
Yes,
I,
yes.
I can see the participants are really enjoying uh, the event. So if you want to take 5 minutes break, we can now.
Yes, yes. If anyone wants to take some break, you can take. Otherwise, if like I'm here only, if you're asking any question, I think 5 minutes will be more. We can take a 2 minute break. Just let me answer this thing. I think Kronecker function, matrix or function. Yes, that is the just the name for the matrix direct form, or the this thing like a Kate-Bra notation that we talked about. This is the thing, that notation of the matrix direct form, that is actually known as, I think here it was there, or yeah. So this particular notation is known as the outer product form, or the matrix direct form, or also the this particular thing like the Kronecker product. So the outer product form is the same name for the Kronecker product. They are the same thing. Okay. What will the ground and the energy state for? If anyone wants a 2 minute break, you can take it. I'm just taking some questions, nothing else. What will the ground and energy state for this superposition? Ground energy and the energy state. Okay, if like whatever yes, of course. See, what I am understanding is that what you are trying to say is basically they are nothing but the ground states and the excited states of that atom. So if we consider the atom or the nucleus or all those things, uh, so basically that means I am somewhere in between, where I can fetch the properties of the ground state, or say, let me not take the ground state only, say the lower energy state E1 as well as E2. So it's somewhere in between E1 and E2. That will be the superposed. These are all there in the physics level already. Now we are trying to, like, yes, okay. Now we are trying to just consider it for the computing angle. That is it. That is what we are trying to say. Where it's a 0 and 1 both. Remember the first day's class. It's only about encoding. Physics is there. Now we are trying to map it to encoding. And what are our cases? The NP hard or the hard problems, which we will be talking about in a detailed way. What are hard problems and all. So for that, there are a combinatorial explosion of the possibilities. And if we have to do it linearly, then that was very challenging. Only the benefit we can get is from the only the benefit that we are getting here is from the basically uh, basically the feature where we can encode multiple possibilities simultaneously using the feature of superposition. Done. Okay. Why coherence term is missing in what coherence you are referring, Satish? Can you please explain that? See here, we're again telling we are a certain like we when we started the second class, all the quantum mechanics postulates we talked about it for computing. Primarily, we are considering an ideal situation where the measurements and all that we are taking coherence, interference. I think you are referring coupling. That is not interference that we talk about here. The constructive and the destructive ones. That is different one. Definitely there are like to visualize encoding if possible whenever we will be doing the day 5, maybe I will be showing that block sphere and all. Then we will be looking into that, looking into more of the like visual representation of these the like superposed states and how the probability I already like discussed that we will be looking into that in the kit itself. So how that like probability densities and all those things they change we will be talking about. But block sphere is a diagrammatic or the visual representation that is there just to visualize the quantum states in the superposed form. And also like Satish question, your question, in superposition in computing there is no effect of that interference directly, so don't mix up things. Coupling is a different thing. So whenever coupling or environmental noise is there, there are a several different, a little different way of measuring it. That is a part of density matrix. We will be covering that. This is the first point. Second is interference. This particular term is related to the only increasing and decreasing of certain quantum states. But again, here we were discussing about the mathematically like increasing or decreasing, and how that particular thing will have a reflection into the number of like quantum state increase or decrease have a reflection into the probability. We are only into that. Okay, I think we are done. We can again, yes. And in superposition there will be no effect of that. That is a position vector, I guess. And this is a like alpha and beta, they are also some of course, like say psi kate 0 and kate 1 together. If you write alpha kate 0 plus beta kate 1, that will be also placed somewhere in the Hilbert space, or that can be represented in the block sphere, which will be having a certain kind of a position vector. But the r equals to x into I, that is only in a simple xy plane, where how with the x coordinate and y coordinate, how you are actually positioning a particular point on the 2D Cartesian plane. That is something with the r. But here, if you remember, here it is a multidimensional or infinite dimensional thing that we are talking about. That this can be anything. Okay, I think interference term last time said in waterfall wave form example for amplify effects. Either amplify or de-amplify for both the things. Yes. Interference term, okay, I got it. Interference term is nothing like interference term. Let me just show you mathematically what I tried to say. Maybe you are thinking there is a separate term called interference term, and they should be taking into consideration while considering the superposition and or entanglement or all these things. But this is not true. Interference basically is something like that. Say, okay, let me just put it here. Say we have something like psi is equals to say a100 plus a201 plus a310 plus a411. Only till this part is superposition. This is already in superposition. Who is in superposition? Psi is in superposition. Okay, psi is in superposition. Right. Now the thing is that, say I have now, if you're asking how to do that, through some quantum gates. Quantum gate, which gate to use? Nothing. That is the quantum logic. Interference, do we mandatorily have to use it? No, it's not mandatory. It depends on your requirement. See, it depends on the requirement of the application, requirements of your specific application. Now, say my requirement was that I will be omitting I will be omitting all odd number terms from my superposition. How to do that? If you ask that question, that is through the simple binary to decimal conversion, and then forcibly not considering, say this is psi 1. So in psi 2, we have to forcibly not take the remaining states of which is the odd number state. That is, I will not be taking this, and this. So I'll be taking, then say alpha 1 dash 00 plus alpha 3 dash 10. Now let me tell you the effect of interference that we have done. So first of all, what this kind of interference is, where we are omitting. This is an example of destructive interference. This is destructive interference. Why? Because we have omitted. Okay, we have like cancelled out few terms out of the superposition. Okay, now there will be a certain changes here because of the destructive inter. What are the changes? So initially this was in uniform superposition. Let me just consider that, so that we can directly measure what is the probability. So what was the probability? So A1, A2, A3, A4, all of these values were half. Yes, half. And probabilities were A4 square, that was 1 by 4, right? But now, considering after destructive interference, like both the even number terms, they are also in uniform superposition. What does it mean? So this was before interference. So after interference, what will happen? After interference, it will be A1 dash square, because now also it has to be like psi 2. It has to also be like obeying the normalization constraint or the basic rule of probability. So it's basically A1 dash square plus A3 dash square has to be equals to 1. So that means A1 to A1 dash square is equals to 1. So A1 dash square, A1, yes, square, it has to be is equals to half. That is 50%. Right? So what will be the value of A1 dash and A3 dash? Initially it was half. Right now it will be 1 by root over of 2. This is the effect of destructive interference. This is what I was trying to say. That interference only affects the number of states. Either it increases or it decreases, resulting in the change in the probability amplitude as well. And similar thing will happen for constructive interference as well. If your psi 1 has, say, A1 0 plus A2 0 1. Let me consider. Can we create this state? Yes, we can create this state. Why? Because what I have said is maximum number of states that can be created is 4, is 2 to the power 2, and this is the number of qubits. So that is 4. But if we want, we can create less than 4 or less than equal to 4 number of states also with 2 qubits. So first of all, we have to understand, we have to agree on that point that this is some quantum state which is in superposition of only 2 states, 0 0 and 0 1, and this can be created. Now whether that is relevant or not, we can do it with 1 qubit, that is a separate thing. But let me assume this can be created, or since we are taking 2 qubit, let me take A310. That is not 4 states. I have only 3 states. Now, considering if this is in uniform superposition, that means A1 is equal to A2 is equal to A3 has to be what? 1 by root 3. Because the probabilities will be 1/3, which is 33.33%. Now, if I again apply something, introduce some ancilla, then just combine it, a single qubit, another we are taking, then applying it with this thing, with a tensor product and all, and through several operations, say list of quantum operations. Okay. If we can get, say, psi 2 as A1 0 0 plus A2 0 1, of course, they will be not exactly A1 A2. Then A3 dash 1 0 plus some new, say A new 1 1. Then what will be the thing? And this is also in uniform superposition. That means the number of states has increased. So this is constructive interference. And then A1 dash is equals to A2 dash is equals to A3 dash is equals to A new will be what? 1 by 2. And the probabilities will be half square, that is 1 by 4, that is 25%. So see, constructive interference actually decreases the probability from 33.33 to 25%. So by increasing the number of states, okay, we actually decrease the probability. So this is your case number 2, say. And your case number 1 was, that by decreasing your number of states, you are actually increasing the probability. What was the initial probability here? It was like 25%. So there is an increase in probability for destructive interference, and there is a decrease in probability for constructive interference. Okay. Now, is it clear now? Those who were having difficulty in understanding the interference? Yes, we are increasing more number of states. Is it clear now? Have you got it, like the interference thing and all, or how it affects the probability or the probabilistic amplitudes? Okay. Any doubt till this part? Any doubt you have? Otherwise, we will enter into no cloning theorem. So there is no doubt, right? Okay. Okay. Let me start it. No doubt. Thank you. So I directly don't remember that QT00, whether you were the whether I covered this or not. Anyway, we have a repetition here. So for those, if you know it, so you can again enjoy it, no issue. And those who are new for QT02, it will be a new topic to you. So I will be starting from the basic for no cloning, teleportation, and super deals, all these things. So no cloning is also a very fundamental postulate or say property of quantum mechanics, as we discussed in the first class of QT02, that man in the middle attack is not possible here because I cannot clone any arbitrary quantum state. I cannot clone or I cannot copy any arbitrary quantum state in quantum mechanics. So the concept was like, so what is no cloning? So definition, you can say this is like there does not exist, there, I'm not talking about any bookish definition, you can follow that. I'll come to the mathematical formulation, but before that, for your understanding, no cloning theorem is there does not exist any oracle or unitary operator, or say in simple words, some machine. Machine means not the physical machine, we are talking about the abstract machines. Okay, abstract machine. There does not exist any oracle that can clone or copy any arbitrary quantum state. So mathematically this means, say you have a Xerox machine. Say you have a Xerox machine. Now if I give you some mathematics paper and ask you to copy that, say Xerox, do a Xerox of that one. So what he will be doing? He will be going to the Xerox machine, will be like putting one blank paper as well as the mathematics paper, right? So you will be putting, like the Xerox machine will be having two inputs. Two inputs. What are the two inputs? One is the one blank paper. So this is where you want to copy. And say one target paper. So this is what you want to copy. Like what I want to copy and where I want to copy it. So of course these two things I have to give to my Xerox machine. And what output you will be getting? Of course you will be getting back your target paper or the original paper as it is. Say this is the original. Target paper or the original paper as it is will be getting. There will be no change. Okay. And the blank paper will be now your another paper. Say the copied paper or the Xeroxed paper. So basically this is your target that you want to do. Right? So similarly here also. Now by the term oracle, I mean some operator. So say this is your unitary operator. And what I'm claiming, or what the quantum mechanics claims, is there does not exist any such unitary operator that can do that. So now if we come to the mathematical derivation definition, so that means say there is a blank state, blank quant. Here we want to copy not a paper, rather a quantum state we want to copy. So definitely we have to. That means consider a blank state. Say a blank state is there which is initialized with gate 0, and there is a original one which we want to copy. Say this is the arbitrary quantum state. And that means there is a unitary operator. Now, suppose I am assuming that this unitary operator exists. So we'll try to contradict the theory. So for that, first I'm assuming that that unitary operator exists. So this will result into Kate psi. That is, this blank will now be having this state information, and the original psi will also be there, right? So this is some, and we are telling that there is a unitary operator u that exists which will do this. Okay. So what I try to prove, like to prove is no unitary transformation of such kind does exist. Now we are assuming what? We are assuming that such u exist. So we will prove it by reductio ad absurdum, which is in easy word, basically this is the proof by contradiction. We'll try to prove that. This is simple proof by contradiction. Okay. Now if such u exist, then that means u on 0 and psi, this is the function, will make it psi psi. Okay. Now let me assume, say this is equation number 1. Now since I cannot talk about any specific one type of gate, there is no gate, this is an operator, so this can be like a sequence of gates. So no one type of gate specifically for duplicating a quantum state, that means if such u exist, because there is no gate, so if such u exist, then in order that is useful, I must have, say for this particular psi u exists, that means I must have the same u, same unitary operator duplicating a different state as well. That is a Xerox machine, right? Say you have giving a mathematics paper, it is able to Xerox it. Now if you give a history paper or electronics paper, if you again have to redesign the cloning mechanism, that will not helpful. That will not be of any use. If it is a generic logic, then it should work for any of the paper that you give it, whether it's a mathematics paper or it is a electronics paper or a history paper. So considering if that exists, that means you can also do this. If it can do it for psi, then for phi as well, it should be able to do that. Say this is equation number 2, right? Now if this is true, if both are true, then let me take an inner product of psi phi. Now, can I write this thing? Psi, then I will be taking this thing extra and psi. Can I do that? Yes. Why? Because this is true, because this is nothing but 1. This is the inner product of two same term. Say, let me show you. Say this is bra 0, which is 1 0 product. This is 1 0. So this is a 1 cross 2 and this is 2 cross 1. So the result is 1 into 1 plus 0 into 0, that is 1. So this is basically an identity operator. Anything inner product with the same thing, we can use that. So that is what we have done. So now let me take it like this, say psi and 0 together, and here also let me take 0 and phi together, and here let me introduce a u dagger u. Can I do that? Yes, because we just have seen for Hermitian and all, U dagger U is nothing but the identity matrix. Why I'm writing not one and identity, because it is all, this is also matrix and this is also matrix. So U dagger U is also I because of the Hermitian logic. Hermitian or self adjoints. So now once we have done that, let me now take this together and this together. So that means it will be nothing be, it can be written as this, and this can be written as phi, and this is only phi. And why we can write that? Because from equations 1 and 2, this is something that we were assuming that they are true. So u0 psi will make it psi psi, and u0 phi will make it phi phi. If that is true, then we can write it as, in this way, inner product of psi phi, that square. Now when, say when this thing psi phi will be equal to psi phi square, this will only be true if two states psi and phi are orthogonal to each other. That is, the inner product of this is basically 0. Then this will be true. Or this will also be true if these two states psi and phi are identical to each other. So orthogonal means this psi and phi are perpendicular to each other, and otherwise they are identical to each other. Why? Because that means either this is the thing, then this is also 1. And if this is 1, then 1 square is also 1. Likewise, some theory is there. But one thing is guaranteed, that observation, the most important observation is here is that psi and phi definitely share some correlation between them, implying psi and phi are not two arbitrary quantum states. Right? Now, what were our assumption? That if there is, there are two different arbitrary states, then I definitely have that Xerox machine or that unitary operator existing that can actually clone both phi and psi. But what we are assuming, considering if such U exists for both psi and phi, we are actually getting some relationships, some mathematical dependency between psi and phi, that either they are orthogonal to each other or they are identical to each other, but definitely they are not arbitrary to each other. So looking from an operator perspective, or say therefore, looking for an operator that can clone any arbitrary state is not possible. Therefore, quantum no cloning is true, or say quantum cloning does not exist. So quantum supports no cloning theory. Okay. Again, let me just pause a little. Let me ask you, Okay. Any doubt? Any doubt in no cloning? We have 15 minutes, so we will be starting with the teleportation. Any doubt you have? No one has any doubt, right? Okay, great. Thank you. Thank you. So, before starting with teleportation, I think we can do one thing, because for teleportation, I need a little understanding of the quantum gates. So, a little alteration of the like syllabus we can do. Oh, yes, I think that will be better for me. Once I cover the quantum circuits, we can do that or gate. Okay, let me start. You got this one. Let me start a little theory. This can be a little boring, but I think this is the best utilization. Otherwise, I have to do a lot of CNOT and all quantum gates, so we'll not be having the full understanding. Okay, so I'm just entering. For now, just hold on with the teleportation and no cloning, teleportation and super dense coding. We will be doing it maybe tomorrow or day after tomorrow. That is in the last class of the first half. So let me just start with the Schrodinger's equation. Schrodinger's equation. Again, I'm telling this is a little theoretical kind of thing of the quantum mechanics. Uh, and but this is in the syllabus we will be covering bit a little. So this is the fundamental Schrödinger equation. This is kind of a fundamental equation of, say, relativistic quantum mechanics. Describing, for now, you should be just having the notion of what do we interpret or what we can interpret from the Schrödinger. That is the target, primary target. Describing the how a quantum state can evolve or evolves over time. So it is the equation governing the state evolution or time evolution of quantum states. So these equations are primarily of two types. What do we mean by time evolution of quantum states? First of all, say time at time t equal to 0, this is something, quantum state, say 0. Then at time equals to 1 unit, this is quantum state 1. And likewise, till the quantum state, say n. So this is at t equals to n time, n unit. And this entire time evolution of quantum states, that how the quantum states are evolving with respect to the variance in time, that is governed by the Schrödinger equation. And there are two different type of it. One is the TDSE, or the time dependent Schrödinger equation. Another one is the TISE, that is the time independent Schrödinger. Okay, so there are a lot of like terms and equations and all. So let me just write that. So for TDSE, it is basically I h cap, then del t of psi r t. This r is the definitely the position with respect to the time t, t is the del del t, you know that, the partial order derivative. This is the reduced Planck constant, reduced Planck's constant, and this is equals to the energy operator h cap and psi are t. So this h cap is basically called as Hamiltonian operator, or also known as the total energy operator. Okay, and this thing, the h cap, the reduced Planck constant, this is h Planck's constant divided by 2 pi. Okay, pi, you know, the normal value of 22/7, and this h is basically 6.62. This is a value of the Planck's constant, and to 10 to the power minus 34 meters square kg per second. Okay, and the TISE, time independent Schrödinger equation, is something when the system's potential energy, from now onwards we will be writing PE, is not time dependent. So this is the thing, h cap psi r, that is equals to E psi r. Where now you see there is no time factor t here associated with this. So the psi r is also called as spatial wave function. With respect to space, that is why it's called a spatial one. You know the temporal and spatial, so this is only the spatial. So spatial wave function. What is E? Is the energy eigenvalue. Okay. And Hamiltonian H cap is nothing but T cap plus phi cap. This is the very like primary equation, where this T cap is the kinetic energy operator. We are just defining today. I don't know how much time is left. I think we almost are done. And this is the potential energy. This is KE operator, and this is the PE operator. Right? And this T cap, kinetic energy operator, this is minus H cap square by 2m into delta square. Okay, this is the kinetic energy operator. So m is the mass of the particle, and this h cap, which is reduced Planck's constant, it is the fundamental constant in quantum mechanics. Okay, and what is this? This is the Laplacian operator. So we will just end with this definition of Laplacian operator. So in three-dimensional Cartesian plane or Cartesian coordinates, this Laplacian operator is basically the delta square del x square, the second order partial derivative. Okay. Okay. So this, like del square del x square, del square del y square, del square del z square are the second order partial derivatives in x, y, and z coordinates. respectively. And what does this give? This Laplacian operator basically gives us an interpretation. So this gives us an interpretation of curvature or spread of the wave function. Spread of the wave function. So let me pause here. At least we have introduced the Hamiltonian operator. First, we have seen in the last 15 minutes what is Schrödinger equation. It's a very fundamental equation governing the time evolution of quantum states in quantum mechanics, followed by the time dependent and the time independent Schrödinger equation. We have seen their basic definition. Then what are the individual constituents present in that definition? What are the terms? What is their meaning? What is their value? We have seen that till that part. Then we have seen in the time dependent one, there is an introduction of an operator called as Hamiltonian operator, right? Which is also the total energy operator, meaning that we can break Hamiltonian into the kinetic energy operator and the potential energy operator. Then we have seen the definitions individually of the kinetic energy operator. And there, what are all the terms? And there we again have introduced another operator called as Laplacian operator. Then we have seen its definition as well. Now tomorrow we will be first covering the entire part, entire physics behind this thing, and a little mathematics, whatever is required for like the quantum computing purposes. We will look into that, and this will also lead us to understand that the how the time evolution will take place with respect to the matrix. So we will the introduction of matrix and why quantum mechanics actually can be interpreted using only the linear algebra and the matrix representation. That theoretical derivation. So how this concept is mapped in the matrix format, that theoretical derivation is the fundamental outcome of the Schrödinger equation and all these things that we will be learning. So tomorrow first we will be covering this part. Then we will be covering the quantum, maybe the quantum gates and quantum circuits. And once we cover that, then we will go back to the teleportation and super dense coding, and followed by the density matrices and a little that thing, quantum technology. So in last 2 days, we will be more or less following this particular structure. Okay. So I want to pause here. I will be sharing all these slides with you. So any doubt anyone have?
Yeah, there are two doubts, ma'am. How do we evaluate the communication when the sender does not have a copy of the message? The second one is, could you please tell me the practical applications of quantum gates?
Bhavna, yes. I think what you are asking is a part of quantum teleportation, or which is again a very primary concept of communication. So please just focus on what we covered today. That is the no cloning and whatever we covered. I will be definitely talking about copying the message. That phenomenon is called no cloning, but this has an application. We will see that without copying also, we can actually communicate some classical as well as quantum information from the sender to the receiver end without copying. We will look into those technology in detail. For that, I just want all of you to understand the quantum gates and circuits. So for that reason, we couldn't start it today. Another is a practical application of quantum gate. Practical application is to write any quantum logic. If you like quantum gates, say where we need, why do we need and or not these gates in classical gates, right? These are the like primary things which are building block behind any programming language. Right now we are into a high level programming language, but for quantum, like high level language also has an assembly level decomposition, right? So the quantum assembly, the QASM, or chasm we call it, that is actually written in terms of the basic quantum gates. So we just place the gates and deduce the entire logic, and all the gates together they form a quantum circuit. And once we have the quantum circuit, we run it in the quantum hardware. Then it becomes an algorithm. So quantum gates are very fundamental. You can assume it like the, say for example, the add. You remember the mnemonics in assembly? We use those kind of thing like carry, then for move, mov, all the assembly languages. So this is a building block to write the quantum algorithm. I hope now it's clear. Okay. Okay. There are no
Yes,
further
ma'am.
doubt. Okay. Okay.
Yeah, only thank you. So doubts are cleared.
Okay.
Yes. Thank you, ma'am, once again for your valuable time and taking out from the busy schedule and completed 2 full hours. And then let's hope that we will meet again tomorrow at sharply at 3 o'clock. So any material will be shared immediately.